last lecture we were finding distances between points, planes, and lines. And we had done 4 of them. Point to point, point to plane, plane to plane, and line to plane. The last 2, plane to plane, meant they were parallel, and the last one, line to plane, meant that they were parallel. That leaves us 2 left to handle. Right? So let me talk about the 5th one. Point to line. So visualize that we've got a point here, P, and you've got a line here, L, and you want to find the distance between them. All right? I'm going to illustrate by example, okay, as opposed to produce a general formula. So the point I'm choosing is the point 1, minus 2, and 1. And equations for the line are x is equal to, not sure what that is, but it doesn't matter. 1 plus 3t, y is equal to 4 minus t, and z is equal to 1 plus 2t. So we want the distance from this point to this line. And then again, it's going to mean the shortest distance or the perpendicular distance. So if I drop a perpendicular over there, let's call that r. Now there's 2 ways you can do it. In the book, example 1123.23, did it one way. And the way it did it was to parallel all the other examples that we've seen so far, those first 4, and the last one, which is yet to come, by talking about projecting or taking the component of one vector along another vector. I did it for that reason, so that they'd all be done the same way. It turns out that that's not the easiest way to do this one. There is an easier way, and it's in exercise. It's talked about in exercise 29. And so I'm going to do it that way here, simply because it's easier, and I want to illustrate then how it's done. All right, here's the idea. Let's take a point Q, any point on this line that you want. All right, let's find one. You agree if I took the put in here t equal to 0, I get 1, 4, 1. That's a point on this line, correct? All right. Suppose I make a triangle here by joining P to Q, right? Call that angle in theta, right? If I looked at this diagram, here's what I want is that there, that D, right? That's the D that I want, okay? Would you agree by looking at that triangle that D is equal to that one over that one is the sine of this angle, is the length of PQ multiplied by the sine of theta. Right? Problem is, I don't know what theta is. I know what P is, that was given to me. I just produced a Q so I can find this vector, but I don't know what theta is. But if you started to think back about 1210, and what's in sections 11.3 and 11.4, suppose I do the following. I put PR here, I put PR, and I put PQ, and I put RQ, QR, sine theta. Suppose I do that vector. Would you agree that this and this are the same? And the answer is no, not likely. Okay, the length of this vector, right, is not likely to be 1. In which case, then that would be destroyed. But suppose I do this, I do that. Talk about putting in there the length of, again, a unit vector. Then all I did was put in there 1. But you may recall from first year that the length of u cross v is equal to the length of u, the length of v, the sine of the angle between them. When you had dot product, it was dot u, v, and cos theta. When it's a sine theta, then that's the length of the cross product. Well, what do we got here? Is sine theta the angle between PR and QR? PR and Q, P. Oops, I wrote down the wrong one here. Okay, wasn't working. That was supposed to be the PQ. All right, so PQ, and yes, theta is the angle between. So this is nothing more than the length of PQ cross QR. Can I find QR? That's a unit vector along the line. No problem. PQ, no problem. All right, so this I can do. So let's do that. So we'll have the length of the cross product of I, J, and K, and PQ. PQ is a vector from P to Q, so those ones minus those ones, 0. That one minus that one, 6. And that one minus that one, 0. Oh, that's nice. All right, that's rather nice. All right, now we're going to take QR, a vector, unit vector along this line. Well, a vector along the line is 3 minus 1 and 2. We need to make it into a unit vector. That means take it and divide it by its length. So let's simply write that off the side here. QR hat is 3 minus 1, 2, divide by its length, 9, 10, the square root of 14. So we'll put in here then 3 over root of 14, and minus 1 over the square root of 14, and 2 over the square root of 14. So we take that cross product, and we take its length, and half what we want. All right, cross product. Do you agree there's going to be a 1 over root 14 that I can pull out? I don't have to carry that through. Okay, so pull the 1 over root 14 out. And then for the x component, we have that one times that one minus that one times that one. That looks like a 12. Then for the y component, this one minus times this one minus this one times that, that's gone. Z component, that one times that, that's gone. Minus 18. Minus 18. I think I said the y component was gone. I forgot to break that down. So we need to have a 0 in here. A 0 and a negative 18. And we have to take the length of that baby. So if we take the length, we're going to have 1 over root 14. Well, we got to pull out a 6. Pull out a 6. What's left is to take the length of the vector 2, giving me a 4 here, and a 0, and a minus 3 here, which is a 9. So the answer then is 6 root 13 over root 14 is the length from a point to the line. Again, this is using the technique in exercise 29 rather than the technique in example 11.23. Example 11.23, there's a couple cross products. It's not nearly so obvious as this is. But so this is different. It's not using components, it's using trigonometry. That leaves us then 1 to go. Line to line. Number 6. Line to line. And I would suggest we break this into 2 pieces. Parallel lines. If the lines are parallel, so we are going to assume that they don't intersect. If they intersect, then the distance is 0. So we're assuming that's not the case. If we're going parallel lines, 2 lines are parallel, and you want the distance between them, why couldn't we just pick a point and do that? Then the distance from this point to that line. Right? Pick a point. On one line, find So that's not wrong. Then all we have to do is the B case, which is, let us suppose they are not parallel. This is perhaps the hardest one to visualize, but I'll get you a formula. So once we can understand how I got it, then we could use the formula if we want. If you don't want the formula, you'll have to kind of go through what I did here. B, not parallel. Which are said to be then skewed. Said to be skewed. Lines in space that are not parallel are said to be skew lines. So let's draw a picture. So here's one of the lines, and here's the other line here. Right? They don't intersect, and they're not parallel. There they are. We want the distance between these two lines. And again, that would mean the shortest distance. Right? And that would also mean perpendicular. That is, there would be a point on this line, and there would be a point on this line, so that if I join those up, that would be perpendicular, that would be perpendicular. Let's call that P, and let's call this one, I want to use the same notation as in the book, P and Q. So there's the distance that we're looking here. Find the point on this line, L1, find the point on this line, L2, such that that line PQ is perpendicular to that line and perpendicular to that line. And those 2 points would exist. The problem is, I don't know how to find them. So the difficulty then is to find that length, not knowing what P is and not knowing what Q is. Well, suppose I pick a point S. Pick any point S on this line that you want. I can easily find it, right? If I give you the equation of this line L1, and I give you the equation of this line L2, then you can easily find your point on that line. What you can't find necessarily is the Q value, but you can find another point. Suppose I were to join these 2 points together. Right? Would you agree that this is a right-angled triangle? In other words, would you agree that PS is the component, or that this is the component of that vector along that direction? That length there is the component of this guy along there. Now what we want is the length of PQ. We want that for that distance. And we're saying here it's the component, or perhaps we should write the absolute value of the component of PS along PQ. But we know how to take components. You take the dot product of this guy with a unit vector in the direction of that guy. That's how we take components. Did that last class a number of times. Okay, let's take a look. Well, S I know, P I don't know, so I don't know this guy. What about that guy? Could you find a unit vector in the direction of PQ? And your answer is yes, you could. Because the PQ vector is perpendicular to this line, and it's perpendicular to this line. And if I give you a vector, if I give you the equation of this line, you can find a vector along it. If I give you the equation of this line, you can find a vector along it. You could cross those vectors. You could produce a vector in this direction, and then you can make it into a unit vector. So I don't have any problem with this guy. But I do have a problem with this guy. The S I know, the P I don't. All right, watch this. Could you find me a point on that line? Answer, sure you could. Not a problem. Give me the equation of L1, you can find me a point on it. All right, let's see now. Suppose I join this, like that. The problem is PS. Oh, would you agree that PS, the guy I'm having trouble with, is equal to PR plus RS? Agree with that? That this vector plus plus that vector is equal to that vector, right? Triangular addition of vectors. So I could, if I wanted, instead of writing PS in here, I could write PR plus RS dotted with PQ hat. I can write, look at it a little more complicated, but let's see if it accomplished anything. What I didn't like about this one was I didn't know what P was. This guy was okay and he's there. What about RS? Yeah, if I find me the R and I find the S, good. What about PR? Oh, rats! I don't know what P is. I don't seem to have accomplished anything. Oh, but watch. Could I write this? PR dot PQ hat RS dot PQ hat. Is that okay? That one with that one and that one with that one, right? Now this one again is okay. What about this one? Well, here's PQ and here's PR. They're perpendicular. They're perpendicular. So this is 0. So what am I left with then? RS dotted with PQ. Take the absolute value. And you got it. So there's a formula, right? So all we need to do is pick a point, do the RS vector. To find this guy, unit vector, vector long, cross them, and make it into a unit vector. All right? How does that look? An example. Let's make up. Did I write one down? No, I didn't write one down. So let's make one up. All right. Distance between the following lines. L1. X equal to 2 plus t. Y is equal to 3 minus 4t. Z is equal to 6 plus t. Line 2. X minus 2y plus 3z is equal to 4. X plus 2y minus z is equal to 0. Agree that this is a line? Parametric equation. Is this a line? Yes. That's a plane. That's a plane. Two planes intersect in a line. I want the distance between those lines. Since I wrote these down at random, I'm praying that they're not parallel. The likelihood of that happening is really, really small that I would actually do that. So let's hope it doesn't happen. All right, what do we need? We need an R, we need an S. We need a point in each line. All right, let's get those. R, point on this line. What would you do? I think I'd put in t equal to 0. 2 and 3 and 6. This one, point on this line. Oh, well, that's not so obvious. What are you going to do? How are you going to find yourself a point in that line? I think here's what I would do. I think I'm going to put z equal to 0 and actually find where this line crosses through the xy plane. So I'm going to put, so let's do this. I'm going to put z equal to 0, in which case I would have x minus 2y is equal to 4, and I have x plus 2y is equal to 0. Right? If I solve those two, I will get the x coordinate and the y coordinate of where this line intersects the xy plane. So this one says that x is equal to minus 2y. I put that into here, I get x minus 2 times minus 2y is equal to 4. And I get then that y is equal to. That's, how did you manage to do that? I solved it for x. What did I do? I put it in the wrong place. Hey, I'm supposed to put put this into there. So minus 2y is equal to 4. Oh, that was nice. Okay, so that y is equal to then negative 1. And therefore x is equal to, y is equal to minus 1, and x is equal to 2. So our point S is 2, minus 1, and 0. That's a point on this line. All right. Now what do we need? That's got me the R, that's got me the S, that's got me this vector here momentarily. I need the PQ vector, a vector perpendicular to both of these lines. I think what I need, therefore, is a vector along this line and a vector along this line, and then I will cross them, and I will have a vector perpendicular to both of them, and I'll make it into a unit vector, and I'll use this formula, and I'll be done. That's it. Right? So V1, vector along line 1. Well, that's the numbers that sit in front of the T's. So we can write 1, negative 4, and 1. That's a vector along this line. What about a vector along this line, V2? You got this plane here, you got this plane here, they're intersecting a line, and I want a vector along that line. We talked about that the other day. If you take the normal to this plane, and you take the normal to this plane, and you cross them, you will get a vector along their line of intersection. So, I, J, K, vector 1, negative 2, and 3, 1, 2, and negative 1. That's going to be a vector along line 2. So what do we get? 2 minus 4. 3 plus 1, 4. 2 plus 2, 4. All right? There's an or. I think I would like to use minus 1, 1, and 1. That's also a vector along. Just these are numbers. Because what am I going to do? Going to make things into a unit vector eventually, so it doesn't matter. What was the idea? We were going to cross this guy with this guy to produce the PQ guy. So another cross product. All right. No, I need that. Okay, I need you. So then, finally, vector, let's see, vector along PQ. It's not necessarily going to be PQ, but if I cross then these two, V1 and V2. V1 cross V2. And V1 is 1, negative 4, 1, and then minus 1, and 1, and 1. Getting therefore minus 5. Minus 1, minus 2. 1, take away 4, negative 3. Well, there. There then is, well, looking back at this now, see that little slippy there? That guy is supposed to be that guy, that's supposed to be a hat. Just happen to notice that now. So we can say that PQ hat is equal to this guy, turn him into a unit vector. Why don't I throw the minus signs away? 5, 2, and 3. Over the square root of 25, and 4, and 9. Now, it might be this, but it could also be that. So maybe we should put that in. 5, 2, and 3 over the square root of 38. Square root of 38. It's not going to matter because over here we got absolute values. So finally, what we want is the length of PQ is equal to, it says RS dotted with PQ hat and take absolute values. RS, from R to S. This one minus this one. 0. This one minus this one. Negative 4. This one minus this one, negative 6. Dotted with plus or minus 5, 2, and 3 over the square root of 38. And we're just about done. So what do we get? Throw away the plus and minuses. Minus 8, minus 18, minus 26, 26 over the square root of 38 is the distance. Provided I make no errors in all these calculations. So this one is perhaps the most complicated. It's not complicated once we got the formula, right? But it was complicated getting that formula. And this can be complicated in here, depending upon how I give you the lines, okay? Here, this one was easy. It's easy to find a point, easy to find a vector log. Here, we had a little more trouble. To find the vector log, I had to do a cross product. To find a point on, I had to put z equal to 0, solve for x and y. But forget about the calculations, the idea. All you need is 2 points, one here, one here. Take that vector and take a unit vector perpendicular to both of those guys and take it out product. Okay? One last topic in this section talks about finding the area of parallelograms and triangles. We all know how to find the area of a triangle. It's 1/2 the product of the length and the base and the height. And when we had that in, say, a plane in the past, that was relatively easy to do. Suppose, however, we have a triangle in space. So visualize that that's a triangle in space. We put axes here. We want to find the area of that triangle. We could do it by saying, look at the following. Drop a perpendicular from B down to AC, and then we can say that the area is equal to 1/2 the length of AC times the length of BD. Now, if I give you the coordinates of A and I give you the coordinates of C, you can easily produce that vector and find its length. We know how to do that. The difficulty is D. I need the coordinates of D in order to find the length of BD. Now, I can do that based upon what we've had in the past. One way would be as follows, but it's not going to be the best way. Is we could find, say, parametric equations for the line BD. We could find parametric equations for the line AC. We could solve them together. We could find the coordinates of D, and then we could find the length of BD, and then we would be done. That happens to be the long way to do it. Here's a better way. If I call this angle in here theta, do you agree that BD is AB, the length of AB, multiplied by the sine of that angle theta? That in this triangle right angle, that one over that one is the sine of that angle theta. Still we have the, so now what we've got is AC, which we can find. That's not a problem, because I'm giving you the coordinates of those two. That's not a problem finding AB, because I'm giving you the coordinates of those two. The difficulty now is, I don't know what theta is. But you may recognize that from your vector stuff. Remember that if I gave you two vectors, U and V, and I crossed them, and then said, let's go find the length of that, there was a formula that said, it's the length of U times the length of V times the sine of the angle between them, where theta is the angle between U and V. Well, that's exactly what I got here. I got this vector, I got this vector, their lengths, and I got the sine angle between them. So this is nothing more than the length of AC cross AB. And know that I can find. Since I know the coordinates of A, B, and C, I can find that vector, I can find that vector, I can cross those vectors, and I can find the length of that vector, multiply by half, and I would be done. So let's take an example. Let's just pick any 3 points in space. Suppose A is the point 1, minus 2, and 3. B is the point 0, 1, and 4. And C is the point 3, 2, and minus 1. Now it doesn't mean that, okay, because I've got A, B, C here, I could choose those two and do the same thing. I could choose these two and do the same thing. All you need is 2 vectors from any one of the vertices that you want. So if we keep and use the ones that we've got here, we could say AB vector, we need the AB vector, we need the AC vector. AB vector, vector from A to B. You want the vector that goes there from A to B. You take the coordinates of B and you subtract the coordinates of A. So these ones minus those would give me a -1. That one minus that one gives me a 3. And that one minus that one gives me a 1. Similarly, AC. We take these ones minus those ones. We would get 2. We would get 4. And we would get minus 4. So those are the 2 vectors. Let's now cross them. AB cross AC. You'll notice that I wrote this direction. It doesn't matter whether you write this direction, it's the opposite direction to here. That doesn't matter because we're going to take the length of the vector anyway. I, J, K. AB, minus 1, 3, 1. AC, 2, 4, and minus 4. Equals X component, minus 16. Y component, minus 2. Check that again. That one minus that one. Okay. And the Z component, minus 4, minus 6, minus 10. So there's the cross product of those 2 vectors. So the area of the triangle now is 1/2 the length of that vector, which is the square root of minus 16 squared plus minus 2 squared plus minus 10 squared. And whatever that is, that's the area of that triangle. Straightforward enough? It says we're going to find the area of triangles and parallelograms. Well, if we made a parallelogram out of this by going like this, would you not agree that the area of that parallelogram is twice the area of this triangle? So the area of a parallelogram should be delete the 1/2, and you'd have the area of a parallelogram. All you have to do is then take 2 adjoining sides, take the cross product, and find the like product. So it's easy for parallelograms, just as it is for triangles.